Hello, everyone, and welcome to today's webinar on DevOps Delivered, deploying Microsoft Azure infrastructure with HashiCorp tools. Please feel free to type your questions during the webinar. We will compile all questions and answers at the end of the webinar and send the results to everyone registered via email. This webinar is recorded, and the recording will be made available after post-processing, usually within 2 days, but sometimes even sooner. Today's webinar features 3 technologies, Microsoft Azure, HashiCorp Packer, and HashiCorp Terraform, and 2 guest speakers. Our first guest speaker is Christopher Boumenot, a senior software engineer on Azure Linux at Microsoft. Our second guest speaker is Eugene Chuvyrov, cloud architect at Microsoft. My name is Seth Vargo, and I am the Director of Technical Advocacy here at HashiCorp. I will serve as both the moderator and a speaker for today's webinar. With that, let's go ahead and get started. At HashiCorp, we build tools that are open source to modernize the data center. You may recognize some of those tools here on this slide, such as Vagrant, which is our tool for building automated development environments, Packer, which is a tool for building automated machine images, Surf and Consul, which are used to do service discovery and distributed key value store, Terraform, which enables us to provision infrastructure, Vault, which is a security tool, and Nomad, which is our application scheduler. All of these tools are completely free and open source, but they tie in and enable our company mission, which is to allow organizations to provision, secure, and run any infrastructure for any application. Today, we're going to highlight 2 of those tools combined with Microsoft Azure for organizations who wish to adopt paradigms such as immutable infrastructure and infrastructure as code. Since this webinar uses Microsoft Azure, it would be really helpful to learn a bit more about it before we move on. Eugene, could you tell us a bit more about Microsoft Azure?
Sure, thanks, Seth. And my name is Eugene Chuvyrov. I'm a cloud architect at Microsoft, and I'd like to spend just a couple of minutes talking about our platform. Microsoft Azure is our cloud platform that is open, flexible, and enterprise-grade. We're seeing an incredible momentum with our cloud offering, and I'd just like to briefly go over some of the numbers that we're seeing. At the core of the Azure is its global infrastructure that spans 38 regions, and the newest ones were launched in France and Korea. And we also have seen an incredible momentum in the last year with over 90% of Fortune 500 companies using Microsoft Cloud. You can see other numbers on the slide here. There's 194 billion external requests made to our app services and 750 million Azure Active Directory users. So our strategy for accelerating the digital transformation and a move to the cloud that many companies are going through is to become a platform of technologies that is trusted, that is open source or open and flexible, and also accelerates application innovation and delivers integrated data and intelligence, data for rich insights within the apps. And I'd like to specifically, in the context of this webcast, specifically talk about the openness of our platform. We're heavily invested in open source technologies and partnerships, as evidenced by this slide. And you can see the HashiCorp logo there in the DevOps line. Nearly 1 in 3 Azure virtual machines is now running Linux, and we support Linux as a first-class citizen. And so why is this important to us? Because it's in the best interest of our customers. In fact, over 40% of CIOs are using open source as their primary strategy heading into this year. Finally, I'd like to mention that we also contribute to open source community, as well as build some of our own services on open source technology, like HD Insight, which is Christopher going to talk about, and Azure Container Service. And this also helps us scale to our customer needs as we rapidly release cloud solutions.
Great, thanks, Eugene. So the first topic we want to talk about today is this concept of immutable infrastructure. Simply put, immutable infrastructure is an anti-paradigm of, instead of modifying, maintaining, or fighting with an existing server using configuration management tooling or by SSHing or WinRMing into the machine, you simply replace it with a new one. In immutable infrastructure, With each change to configuration management, each time a user logs onto a machine, the level of confidence in the state of that server decreases. And this is why we often hear folks in the operations field say, I don't know, let's just rebuild it from scratch. Even more so, though, as those iterations happen across your fleet of servers, the parity between machines also decreases, meaning the probability of an inconsistency between two front-end servers increases over time as configuration management fails or someone accidentally made a config change. And that means that a subset of your customers are hitting an application server or a back-end service that behaves differently than its peers. When we compare that to the immutable infrastructure paradigm, that problem doesn't exist. Now, that doesn't mean that build time failures won't happen. We'll talk about that in a little bit. But it means that every instance of your application is exactly the same. Every server that you're running has the same configuration because you've built a precompiled image that you're deploying over and over again. Because of this, immutable infrastructure is much faster. We don't have to wait for configuration management like Chef or Puppet or Ansible or Salt to run for 30 minutes. We don't have to install packages or download configuration. We simply launch the image. It also allows for greater parity. We can very quickly scale out and have multiple machines that are all behaving exactly the same. But the downside is that immutable infrastructure needs automation. It's incredibly slow to produce these images manually, and you need a solid automation framework in order to be successful. And that's one of the reasons we built Packer. Packer is a tool for building automated machine images. A machine image is a single deployable unit that contains pre-configured operating system and software. A machine image could also be thought of as a Docker container, which is an abstraction of the OS layer and provides isolation more at the user land space. But I know what you're thinking, yuck, golden images. Why have DevOps folks generally been against golden images? Well, there's a bit of history here. You see, golden images used to be the way. They were quarterly, unchanged, and blessed images that were managed by the data center operations team. They would deploy those onto bare metal servers, and it would take quarters or sometimes even a half of a year to get a change in. If you wanted to upgrade the version of Apache or you wanted to install a different package, it would take 6 to 8 months for that to complete. As a result, any changes were slow and frustrating. And that was because the tooling was not mature enough to get us to a point where we could automate those machines. Fortunately, modern configuration management, tools like Puppet, Chef, Ansible, and Salt changed that for us. They allow us to very quickly codify the state of a machine and then provision that machine over and over and over again. Simply put, ops without machine images is like applications without binaries. There's no promise of reproducible builds and operations, and there's no binary-like snapshots. Let's look at a typical application lifecycle. You take some source code, maybe it's some C or some Go or some Ruby, and you compile that into a binary. It's pretty simple. And maybe there are some dynamically linked libraries or dependencies that you're linking to. If for some reason one of those dependencies changes or becomes incompatible, a new version, a different API, a different operating system, the binary fails to build. This binary never makes it into production. The Jenkins server or your CI server is going to fail the build. You're never going to put this in the hands of customers. Now let's compare that to the mutable server lifecycle. The goal is to take a new server, what we call a base server, like a base Ubuntu 14.04 or 16.04 instance, or a Windows 2016 server, and move it into a ready state. And in order to do that, there's a number of things we have to do. We have to install some packages, we might have to configure the network layer, and we might apply users and different configuration management changes throughout that lifecycle. But each of these is a single point of failure. Packages upstream might change. Is everyone locking their packages to exact versions? What if that particular CDN is down? What if there's an unreliable network where we have the ability to download a package is just restricted? What if configuration management has changed and that's introduced a breaking change? All three of these lead to failure. The problem is that this failure is happening in front of the user. This machine has already been added to the load balancer, it's already running, and then we run config management on it, and all of a sudden that machine is different, but it's in the path of customer downtime. When we compare that to the immutable infrastructure or the machine image lifecycle, the goal is still the same, take a base server and move it to a ready state, but it just happens. And this seems like a little bit of magic because I've suppressed some things from this slide. But the reason for that is that the build configuration is moved from runtime, which is in the path of downtime where users are interacting with the service, to what we call build time, which is whenever you're actually producing this machine image. This means you never deploy or taint services in production, which introduces a higher parity with both development and a more stable production environment. So how do we do that? Well, Packer produces machine images from a configuration file, and it provides a single workflow regardless of your role or technology. Now, I know what you're thinking, well, that means, Chef, Puppet, Ansible, Salt, they're dead, nobody needs them anymore, and that's not the case. In fact, Packer embraces modern configuration management, Chef, Puppet, Ansible, Salt, Bash, PowerShell, whatever you want to do to configure these machines, because machines still need to be configured. Where Packer differs is that it transitions those failures from runtime in the path of downtime of the customer to build time on a local CI server or even your local laptop where you're building Azure machine images or Docker containers or VirtualBox or VMware images. And if that fails locally, which it will happen, you're still going to have upstream package failures and unreliable network, but it happens outside of the customer's viewpoint. It might block a release, it might slow down some acceleration and agility, but ultimately the business continues to operate fully functional. Because Packer parallelizes all operations, you can create the same machine image between all of your staging environments, across multiple clouds, and even in development by creating things like Vagrant boxes or Docker containers. One of the many builders, which is a pluggable component of Packer that is supported is Microsoft Azure. And to talk a little bit more about the Packer and Azure integration, I'm going to hand it over to Christopher, who I introduced earlier from Microsoft.
Thank you very much, Seth. My name is Christopher Boumenot. I work for the Azure Linux team at Microsoft, and I'm here to talk to you guys today about Packer on Azure. To kind of motivate this discussion, I wanted to briefly discuss a case study for this, an example of where we're using Packer inside Microsoft. And to give you some context about that, I want to teach you about HD Insight a little bit. So Microsoft HD Insight is a fully managed and supported 100% Apache Hadoop, Spark, Hive, HBase, Kafka, and Storm clusters. The idea behind it is with a few clicks of a button, you can have any of these clusters up and running. It's pay as you go, so pay for only what you use. We have per hour billing, so we see a lot of instances where you spin up and spin down, and we give you 3 nines of SLA. If that still doesn't give you enough context, the summary of all of this is it's for working with big data. I think Seth did a very good job talking about immutable infrastructure, but I wanted to reinforce the concept because it's extremely important to us, especially in context of HD Insight. We are constantly churning clusters up and down because of the model that we have. It's the promise of the cloud, the elasticity, the ephemeralness of the machines. We have to support that concept. One of the things I think that's very important about immutable infrastructure is it's the things that it frees you up from. One of them is a click of a button to rebuild the entire world. It's an amazing thing to be in the situation of you hit one button and you have a 32-node Hadoop cluster spun up for you and ready to go. The other thing that I like about immutable infrastructure is the idea that the recipe is baked in. You know exactly what you're going to deploy. You know exactly what versions are out there, what customers are consuming, and you have very good context about that. If you want to make one change, you can deploy that change immediately from start to finish. You're not paying someone to kind of SSH into the box, make some small tweaks and configuration changes. You know exactly where you are at the start of the world. I think to reinforce that idea of the recipe too is the strongly identifying who you are and what you've shipped to customers. So if a customer tells us they have a problem with Hadoop, for example, we can reproduce that environment exactly. That immutable infrastructure facilitates those things like replication, which is if I deploy for customer X and I want to deploy the same exact thing for customer Y, it's trivial. The portability and mobility idea is very powerful to us too, that Packer enables. So Packer is not technology specific, it supports many different things. If we wanted to take our technology and move from one cloud environment to another, or move from Azure into Hyper-V, for example, those types of things become very attainable. When we were out there looking at different technologies, we evaluated Packer, we started using it, and we were very successful with it. And we kind of came to the conclusion that Packer was the best tool for the job. The thing that really enforced that for us, though, was our customers came to us and said, Microsoft, you need to support Packer. What is the Packer story on Azure? That was a very strong motivator for us and was like, yes, Packer really is the best tool. The other thing we really enjoy about Packer is the open source software aspects of it. This is becoming more and more true within Microsoft as well as people are getting the open source bug, which is the shared community, the experiences people are having. When we walk into the Packer community, you can see that everyone is trying to solve very similar problems, perhaps on different technologies, but regardless, the solutions they're looking for, they can be shared across. So if our customers are gravitating towards one type of solution in Packer, we can try to duplicate it in Azure and try to make our story better. The other thing that I personally like about it, because I am the person who contributes the Azure support for Packer, is the direct interface I have to customers. So when a customer is having a problem, I can interface with them directly, I can talk with them, work through it, and figure out what's going to help them get unblocked and be successful. So walking away at the end of the day when we have a definitive shared success with our customer, I think is a great feeling. The other thing I wanted to talk about too was our Packer process. So how does Microsoft internally use Packer? And going back to the HD Insights, how do we get to HD Insight with that immutable infrastructure built with a Packer, or built with Packer? So the very first thing we do is we start with an Azure Linux base image. So I work for the Azure Linux team. We ship a base images to all other parties within Microsoft that want to build Linux services. We start with a standard distro from the Azure Gallery. We add in a monitoring daemon, which allows us to have telemetry for all the services we ship that plugs into the standard Microsoft backbone. We add things like a security pack, so virus scanning and port scanning and network firewall rules. Then we add a few tweaks to the system, so specifically things like Microsoft Certificate Authority that we use internally. How do we embed that into the image? The nice thing is that when people pick up this image after our Packer build is complete, they kind of get all this goodness for free. They don't realize they have it, but everything just kind of works, which is a great feeling as well. HD Insight then comes along and they execute another Packer build on top of this base image. And they add in their own secret sauce, which is, well, not so secret because it's the Apache solution or it's Storm or Kafka. They're baking those into them to make their immutable infrastructure for their customers. I wanted to set up too for the demo I'm going to do on Packer on Azure with kind of some of my thinking about how I would tackle a problem normally. I usually go through 3 phases. One of them is the make it work step, which is it works on my machine, I have the end-to-end experience, I can now examine and say, what are the things I missed, what are the things that are important for the solution to work, how do I actually get better knowledge of that, get the experience. I think that's mostly the very first thing I ever do. The next step is the make it automated step, which is, all right, now it works on my machine, how do I make it work on your machine, or how do I ship it into the CI server and make sure it's going to be successful there? And how do I ship it to customers and make sure they're going to be successful? The third step, which I think is optional based on where you are, not everyone needs to scale it to tens, hundreds, or thousands, tens of thousands of machines, is the make it scale step. Generally, there are differences between making it automated and make it scale. If you have to think about those types of things, usually that's my last thinking. The other thing I want to talk about is we notice a lot with our GitHub issues, the customers have a difficulty onboarding to Azure, and some of the sticking points they typically hit are, what is a resource group? What is a blob? It's the terminology. How do they understand what the terminology is? Like, for example, in SPN, it's an acronym. So if I told you it was a service principal name, it probably wouldn't still be intuitive what that actually means. It's a service account, but still, it's something you have to learn and understand. With experience, that helps. Experience will help that. The other thing that we face with Azure, or some of the difficulties we see from our customers, is the various IDs that Azure has. And there's a lot of GUIDs, and the GUIDs don't really have semantic information. They're just random numbers, and you're staring at them. Like, what is a subscription ID? What is an app ID? What is an object ID? What is a tenant ID? What are these values, and where do I need to use them? How can I use them to be successful? So for my demo, I wanted to focus on the make it work scenario. And my goal is to get people to be able to download Packer, start with our example build, and be up and running as quickly as possible. The other thing I'm going to do to motivate you is that Azure gives away $200 in free credit for you to use for up to a month. So that one-time setup fee gets you unblocked, and then you can start using the Packer demo right away. There's 2 other things you're going to have to set up that I've set up ahead of time for the demo, which is a resource group and a storage account, and I'll walk through those briefly as well. The example I'm going to use here is the Ubuntu quickstart.json. This is a recipe that we ship in the Packer repo on GitHub, so if you go there and look at the examples, there are many others, but this is the one I'm going to use, and you can download this one right away and be successful. The other thing I'm going to show you is the device login flow, which is we're going to skip that service account creation, that SPN creation. So again, avoiding more of the IDs you would have to actually get knowledgeable about to be successful. All right, and with that, let me go ahead and pop into the demo. So I have downloaded the Packer executable from packer.io, and if you look at the version information, I have the latest version, 0.12.2. The other thing you will notice is I have downloaded the Packer recipe, and I'm going to start the demo right away because it's going to take about 10 minutes, which will probably exceed our time. I'm going to set some environment variables, which will tell Packer what it needs to know to build, and I'm going to go ahead and kick off the build. And this is where we get into our first device login flow. So this is how we're avoiding some more of the complication with the process, some more of the IDs you have to learn. This is telling us we need to log in or go to this website and add this ID. So I'm going to go ahead and add that address, and I'm going to copy this code. And it's saying, do you want the Packer for Azure application to act on your behalf? Yes. I'm going to log in with my standard Azure account. And now that we've successfully signed in, the Packer build will kick off, which it has. So while that's running, let me review what I just did to bring you up to speed. So there were 3 pieces of information that I had to provide to Packer to make this recipe successful. One is the subscription ID, and then the other 2 are the resource group and the storage account. So the storage account is where the virtual machine image will be stored. So if I go back to the portal and I look at my resource groups, I have that resource group that I typed in, which was this HashiCorp Packer demo. If I drill into this, we can see that we have my storage account. My storage account information, if I drill into that, we can see that there's a couple of folders, directories here, and we have all the information. So this is where our virtual machine will end up eventually once the build is completed. There's a few pieces of information that I want to note here, which are the subscription ID we used, the location, so we want to make sure the location of our storage account agrees with where our virtual machine will be built, and the resource group name. Okay, let me return to the recipe and walk through that. The recipe has 3 things I think that we should focus on: the variables, the builder configuration, and the provisioners. The variables, as you saw me use, are the actual configuration information that's going to drive this instance particular to you. The builder is where we set up Azure ARM, the builder we're using in this case. Then there's the variables that we plumb through. This information determines where the virtual machine image will live in the storage account, basically the folder structure. In this case, we're building a Linux image. And the way we define what Linux image we're going to use is based on this image publisher, image offer, image SKU. So in this case, I decided to build an Ubuntu server 1604 LTS. The other thing that's important is the West US. So again, our West US location has to agree with where our storage account is. And the VM size, this is one of the moderately sized newer VMs that we have, which is appropriate for this type of demo. The third thing that's important to you is this is where you bring your expertise and your secret sauce. This is a very plain vanilla Packer recipe in the sense that it doesn't do very much. If you're familiar with Debian or Ubuntu, you notice that the apt-get update, apt-get upgrade. What this is saying is download all the latest package information and please upgrade to the latest versions that are available. The next thing we have is this user bin y agent-force deprovision. So this is where, and this is particular to Azure, where we clean up the virtual machine and prep it for redeployment. If you're familiar with the Windows process with sysprep, it's very analogous, except much, much lighter weight. Now, let's go back over to here and look at some of the text that's kind of flown across. What I wanted to highlight was what are the steps that the builder is actually executing. So every new step the builder executes is delineated by this fat arrow, a little bit of text, and the ... And then underneath that is our variables that are particular to that step, that are important to that step. One of the things you'll notice is this resource group name. And then there's this value right here, Packer resource group, and then some random ideas. The way the Packer builder works for Azure is it creates a temporary scratch space for you, populates it with resources, executes your provision steps, and then takes a snapshot of your VM that you can then deploy as a virtual machine image. So if we go back into our portal view and we look at our resource groups, you'll notice that there is now a resource group called Packer Resource Group ZWH, which corresponds exactly to the one that we had in our Packer build output. And if we go into there, we can see that there are some resources that we've created for you. Now these resources are all temporary, they're scratched. As soon as the Packer build is done, they will all be torn down and thrown away. The only thing you'll be left with is your virtual machine image. We can see that we created a virtual machine, a public IP address, a network interface card, and the actual network that you'll be on as well. The other thing I want to do is, where will the virtual machine image land up? So if we go back into our storage account, and back into, if we go back into our storage account, the virtual machine image is going to end up in the systems directory, Microsoft Compute Images, and this is the one that I've created ahead of time. This is where the actual virtual machine image will be created. And once the artifacts are in Azure, they're ready to be launched. You can launch them via the online portal, Azure CLI, or using an infrastructure as code tool like Terraform. And I'm going to hand it back over to Seth to talk more about Terraform. Thank you.
Great, thanks. Great, thanks, Christopher. Now that we know how to build machine images using Packer, how do we deploy and provision them? Well, Terraform is another free and open source tool by the folks here at HashiCorp that enables you to write, plan, and create infrastructure as code. Terraform enables you to safely and predictably change, create, and improve running infrastructure. It codifies APIs into declarative config files that can be easily shared among your team members. It can then be treated as code, edited, reviewed, and versioned. The concept of infrastructure as code is not something that's unique to Terraform. Terraform uses configuration files to capture all of your infrastructure dependencies and then executes those to create, update, or destroy infrastructure and manage the lifecycle of that infrastructure. Because of its declarative VCS-friendly integration, Terraform enables teams to collaborate and share infrastructure changes the same way that application developers share application code. The easiest way to think about Terraform and infrastructure as code is stealing everything that application developers have had for many years and bringing it into the operations space. Things like linting, continuous integration, change review, pull requests, all of that are things that application developers have been using for years, and by capturing our infrastructure as code, we're able to leverage those existing tool chains and bring them into our infrastructure management workflow. One of Terraform's biggest strengths is its ability to provide a safe workflow. It provides a consistent experience regardless of underlying technologies or job role. Terraform provides the same workflow whether you're using Azure, AWS, GCP, on-premise, or all of the above. And it provides that same workflow regardless of whether you're a designer, developer, sysadmin, DevOps engineer, or CEO. Lastly, and probably most importantly, is that workflow is designed to be very safe. By separating the plan and an apply phase, Terraform allows for safe and sane infrastructure lifecycle management. Terraform includes a dry run mode, which we call the planning phase, which allows you to see what changes and what operations Terraform will make before making them. You can then apply the result of that plan to actual provision real infrastructure production changes. Since all of that infrastructure is captured as code, it's reproducible across many different platforms. You could use the same set of Terraform configurations to build development, production, and maybe QA or staging environments. So I'll ask a hypothetical question to the listeners. How many of you have long-lived staging environments that cost hundreds of thousands of dollars but are only used 2 or 3 times a day? Or maybe you have the opposite problem, where you have one staging environment, but developers are constantly waiting in a queue to get their changes tested and reviewed. With Terraform, developers can quickly spin up their own dedicated staging environment that is an exact replica of production in a single command. When they're done, that environment is destroyed. This simple practice has saved organizations thousands of dollars on infrastructure costs per year and solves both of those previous examples that I described. Because Terraform codifies and parallelizes these operations, it's very, very fast. It's often possible to spin up an entire production infrastructure in just 5 to 10 minutes. Because the configurations are also code, it's possible to create shareable components, like modules, and combine different configurations across different cloud providers. We know that many of our customers are not just moving to cloud, but they're moving to multi-cloud or hybrid cloud, where they're operating across multiple public cloud providers. Maybe they have your own internal cloud, and then some on-premise or bare metal. It's important to be able to combine that because the modern data center is complex. You have third-party DNS providers. You might be using a database as a service from a third party. but ultimately all of those make up your infrastructure. So it's important, and one of Terraform's goals is to be able to codify and capture all of that in a single configuration file so that you can quickly spin up and destroy and reprovision your infrastructure resources. So what does that configuration look like? Well, let's take a look at an example through the Azure portal. Getting a public IP address. So the following examples will all use this notion of getting a public IP address or acquiring a public IP on Microsoft Azure. The first and probably the most visual way to do that is using the portal, which is the screenshot I have here. You can either search or you can click through the different hamburger menus and create a public IP address. You give it a name, you tell it whether it's a dynamic or static allocation, pick the resource group and the location that you want that public IP address to be provisioned in. Obviously, this is great, it's very visual, but it tends not to scale well. You can't really automate clicking around on a UI, and it's not really great for teams. Another common method is to use a CLI tool like Azure RM CLI or the PowerShell plugin. This example here uses the PowerShell plugin to allocate a public IP address on Azure. So the same thing that we saw before in the web UI, but here we're using a command line interface. And this is great because we could check this into source control. We could collaborate on this, but there are some downsides here where, now that we have this public IP address, how do we associate it with other things? We saved it to a variable, but then there's a certain order of operations that have to be maintained. Finally, this is an example of Terraform's configuration. Notice that Terraform's configuration is a format, not a command. So unlike the previous example, which actually ran a PowerShell command, this is just a config file. It's a configuration file, a plain text file on disk. It's a declarative format that can be treated as source code. So we could check this into GitHub or GitLab or Bitbucket. We could easily version it. We can check in different changes and collaborate on it. You'll notice that I'm passing in the same variables, so the name of the public IP address, the location, and the resource group, just like we had to do in the CLI and just like we had to do on the online web interface. But where Terraform's power really comes is its ability to compose these resources across multiple cloud providers to capture all of your infrastructure as code. As infrastructure increases in complexity, the order of operations is incredibly important. In this simple example, the order of operations is important. I'm creating a DNS record and a provider known as DNS Simple. They're just a public DNS company. And I want the A record of that DNS, which is HashiCorp.rocks, to point to the public IP address of the Azure public IP that I provisioned. I can't create that DNS record until after I've provisioned the public IP address. Why is that? Well, that's because we don't know what IP address will be allocated. Since we're choosing a dynamic allocation, Azure is going to determine, you're going to get the IP address 1.2.3.4. Since this is dynamically assigned, I cannot create the DNS record until after I create the public IP address. Even though I put, in this example, the DNS record above the public IP resource, Terraform reads this configuration file and builds a graph and correctly determines the proper order of operations based off of the interpolation. It does this through the little purple section there, the interpolation, by saying that the value of our DNS record is the public IP address, the result of the public IP address. Terraform knows that the DNS simple record depends on that Azure RM public IP, and it uses that to not only provision, but also order the operations and maximize parallelization. So Eugene, could you tell us a little bit more about how Microsoft and HashiCorp are working together to expand Azure's coverage?
Sure, Seth. And I'd like to briefly set the stage for Seth, who will actually go into the demo of deploying a production-ready workload into Azure using Terraform. So let's talk about the two important things that I'd like to cover is basically the state of the partnership today and what you can provision into Azure using Terraform now. Next slide, please. Okay. So I think the two important points I'd like to make is that you can start provisioning production-ready workloads using Terraform today into Azure. There are 16 Azure resource types that are supported. It's enough to get going with a variety of production workloads. And the second point is that we have partnered with HashiCorp to ensure that we deliver support for Terraform in Azure, very similar to the world-class support that Packer has today. And so I also wanted to give a huge thanks to the community that has contributed to this effort of actually implementing various Azure providers or Azure resources in Terraform. And so let's take a look at what's available, what kind of infrastructure you can provision into Azure using Terraform today. Now, on this first slide, we have infrastructure as a service pieces. So within the virtual machines, you can provision, obviously, virtual machines themselves. There's support for scale sets, VM extensions. Then you can also provision virtual networks and define subnets, public IPs. You can define network security groups, as well as other things there. You can deploy a load balancer, which would allow you to configure address pool rules and probes. And this is the demo that Seth will actually do, is deployment of multiple virtual machines with a load balancer in front of them. And finally, certainly storage is extremely important, and you can provision that using Terraform today as well. On the next slide, we have Azure DNS. There's support today in Terraform for Azure. You can also do provision containerized solution using our service, the Azure Container Service, which is also open source, by the way. Then there's support for CDN and Redis. On this next slide, we also illustrated that in addition to the IaaS pieces, there's also support for platform offerings on our cloud. So today, you can provision Azure SQL database and Azure Search. And additionally, support for things like Key Vault, and then there's those elements called template resources, which basically you can also pipe a basic ARM template into Terraform script for those resources that may be not 100% supported yet. So to kind of summarize and set the stage for the demo is next slide, please. So I have started working with HashiCorp probably about 8 or 9 months ago, and I have seen a lot of providers being developed and enhanced in this time frame. So there's definitely quite a bit of momentum for Azure support within Terraform. And again, I wanted to make the point that both companies are committed to making Terraform support in Azure world-class, very similar to Packer, as we saw in the demo that Christopher did. We're also looking forward to community contributions. And finally, before actually handing it off to Seth, on the next slide, there is an alias that we have set up because of our commitment to world-class Terraform support in Azure. We would like to request your feedback. If there's specific requests that you would like to see us implement, please use this alias to send email, and we will definitely address that quickly, or as quickly as we can. And there's also a blog that has been posted for if you're just getting started with Terraform on Azure. As Christopher mentioned, there's a couple of pieces that need to be set up that are specific to our cloud, such as service principal, etc. And this blog helps you get going with that. And now over to Seth to demonstrate deploying production-ready workloads using Terraform for Azure.
Great, thank you, Eugene. So what webinar would be complete without a live demo, and hopefully it works as planned. So I'm going to escape out of the slides here and jump into a terminal. So the gist of this demo is I'm trying to demonstrate that Terraform and Azure both support the ability to provision like a modern infrastructure stack. So what I've done here is I've provisioned a DNS record that points to a public IP address that points to a load balancer that then has some instances behind that load balancer in a private subnet, and they're just serving a static web page. They could be serving, a dynamic application like Ruby on Rails or Django, but right now they're just serving like a static Nginx web page. So let's take a look at that file here, and we'll run through it together. So the very first thing I have to do is I have to configure Azure. Just like you have to configure the CLI or you have to configure any API call, you have to provide the various credentials to Azure to be able to authenticate and make API calls. Under the hood, Terraform's just going to be making API calls, so we need to provide those credentials to Azure. Next, I'm creating a resource group. A resource group in Azure is like the top level grouping of all your resources. So all of the things we build are going to belong to this resource group. It's possible to create more than one resource group, and you can communicate across resource groups, but for the purposes of this demo, we're just one resource group, and all of our things will live inside of that resource group. Next, I'm creating a virtual network. The virtual network is where the IP space where all of our instances and anything that has a network interface will live. Within that virtual network, I'm creating a subnet. So I created a virtual network that's in the 10.0.0.0/16 space, and then I'm creating a subnet, which is in the .1.0/24 space. Again, I'm putting it in the resource group, and you'll notice that there's this interpolation syntax, the dollar curly brace. That's building the order of dependencies. It's telling Terraform, do not create the subnet until after you've created the resource group. Do not create the subnet until after you've created the virtual network. And this makes sense, right? We can't create a subnet inside of a virtual network that doesn't yet exist. Next, I'm creating the public IP address. The public IP is going to be inside our location, inside the same resource group, and I'm giving it a static allocation. And next, I'm creating a network interface. And this is something that I like to point out because it caught me a little bit off guard in having worked with other cloud providers. In Azure, network interfaces are a first-class citizen. So if you've worked with other cloud providers, instances and computes and load balancers, they come with their own network interface. And the size of the device that you're provisioning determines the type of network interface and the number of interfaces you get. In Azure, interfaces are their own top-level thing. They're a resource the same way that you have instances and load balancers. So it's possible to share network interfaces. It's possible to over-provision or under-provision them. You have a lot of control over the network interfaces in Azure. So here I'm creating a network interface, and I'm actually creating more than one of them. By using this count attribute, I'm telling Terraform to create n number of network interfaces, which is currently being controlled by a variable, and the default value there is 3. So I'm going to be creating 3 network interfaces. They're going to be named demo interface 0, 1, and 2. They're, again, in our same location and resource group as before. And then we give it an IP configuration. So I'm giving it a name, the subnet, which is the subnet I identified as earlier. I'm telling it to acquire its private IP address dynamically. And then I'm adding this network interface to the backend address pool of the load balancer. So what that means is that anything this network interface gets attached to will also be in the backend of the load balancer, which means the load balancer will send traffic to this network interface if it's healthy. We'll determine health in a little bit with the health probe. Next, we actually create the load balancer itself. So I'm creating a load balancer named LB. I'm giving it, again, the same location, same resource, and I'm giving it a front-end IP. So previously we assigned back-end IPs. That's where traffic goes. Front-end IP is when the traffic comes from. So this is the incoming request. And the incoming IP address is that public IP I asked for earlier, and I'm telling it to assign its own IP dynamically. Next, we create a load balancing rule. This is not broken. Next, we create a load balancing rule where I'm saying all of the traffic on TCP port 80 should be sent to the backend port of port 80, and it should be mapped to the default IP config. And that's the same IP config from above. So what this is this is a load balancing rule which says whenever someone hits the load balancer on the front side, the front end IP, to route that traffic to port 80 on the backend IP. And then lastly, and probably most importantly, is that we have a health probe which tells the load balancer how to check if the backend instance is healthy. And this is a health probe that's just checking the HTTP protocol on / and make sure that there's a 200 level response that comes back. If for some reason one of our instances is unhealthy, we don't want to send traffic to it, and that's where the health probe comes in. Next, we have a backend IP address pool, and this is just going to be attached to our load balancer. We have an availability set. An availability set is a way to dictate that a group of machines, virtual machines, aren't on the same physical set of a failure domain. So when you put machines in an availability set, what you're telling Azure is, hey, I don't want these to be on the same power source or power grid. I don't want them to be in the same physical rack. So I want to maintain availability in the event of a downtime or in the event of a physical failure. Next, I'm creating a storage account. So you heard Christopher talk about storage accounts. This is where the storage for our images will live. I'm creating it just a standard LRS account. It's in the same resource group in the same location. And you'll notice that the name is this random ID resource here. This is because storage accounts in Azure must be globally unique within the whole scope of Azure. So everyone who's using Azure has to be having a unique storage account name. So what I've done is I've used a Terraform resource called random ID, which will generate a random UUID that's prefixed with the word demo. So you can see an example up here, like demo, 3 Delta 1 Bravo 9 Delta 4 7. That's what the storage account would be. Does this guarantee that there'll never be a conflict? No, but it helps us be able to reproduce and reuse these configurations over time by allowing Terraform to generate a random ID for us. Next, we create the storage container. This is where the data of the instance is going to live. You can think of it as like this is the hard drive for this virtual machine. And then lastly, we create the virtual machine itself. And notice that we're creating more than one of them. You can see that here through this Azure RM instances. That's a variable, defaults to 3, so we're going to spin up 3 instances. Same location, same resource name. We're giving it one of the network interfaces that we created before. This is some advanced Terraform configuration, which says, give me all of the network interfaces as an array, and then get me the one that's at the current count. So the first network interface will get assigned to the first VM, the second to the second, the third to the third. Standard AO, VM size, we're putting it in the availability set. I'm spinning up a 1404 Ubuntu server. We're giving it the storage OS disk in the storage account and the container that we created before. I'm telling Azure to delete the disk on termination, so we don't want the storage account to maintain the data even after we delete the VM. And then I'm giving it an OS profile. So this is the login information, the username and the password for logging into this VM if I wanted to, SSH or WinRM in. And then I'm giving it some custom data. This custom data is read from a file, which is just install.sh, and that's going to install Nginx and provision out an initial index.html file for us. So here you can see that this comes in at about 155 lines of code. There are some comments in here, so it's a little bit less. And this is provisioning what we would consider kind of like a basic multi-tier web application, front-end load balancer, back-end private network with a configurable number of instances. I could have put these in a group that would automatically scale. I call it a scale set in Azure. But for now, I chose to just hard code. There's 3 of them. And we can actually use Terraform to scale those out in the future. So I ran this ahead of time. It takes about 5 minutes to provision this. But I'll go ahead and run the Terraform plan phase. This will show me what will happen. And because there's no changes, we should say, OK, Terraform didn't detect any changes in your infrastructure. As a result, you won't see any differences. So let's fix that. Let's go into these variables, and we'll change the number of instances from 3 to 4. And now when we run Terraform plan, it's going to refresh the state. So it's going to go out to Microsoft Azure and say, hey, which of these instances exist, which don't? And here we can see that it's going to add 3 resources and change 3 resources. And if we scroll up here, we can see the summary here. It's going to add a new network interface. It's going to add a new storage container. It's going to change the interface IDs here. It's going to add a new virtual machine to the list, and then it's going to update the load balancers and stuff in the back end. So I'll go ahead and kick this off. And while that's going, where is this? Everyone can go here. Yeah. So this is the, I'll make this really big. This is the actual DNS record that's been provisioned with using DNS Simple, Azure's public IP. This is something you can hit in your browser, so all of the attendees can actually go here, and I'll open up a Chrome window and toss that over here. So if I go to HashiCorp or terraform.hashicorp.rocks, I should see a page like this. So if you refresh this page, you'll notice that we're being bounced between a few different node IDs. And as people visit this page, you'll be randomized round robin. And there's some information on this page to send you to other websites. So for example, here's Terraform's website. That'll take you to Terraform, where you can see all of the documentation about Azure-specific things or any of the other on-premise or public cloud providers. There's a link here which will take you directly to the sign-up page for Microsoft Azure. There's a link here which will take you to the source code for the code that I just ran. So this is public on GitHub. I made it public about 20 minutes ago. The templates that I'm using, the config that I just ran through, this is all completely public. You're free to take a look at it for yourself, fork it, make any changes, whatever you'd like to do. And then lastly, I just want to thank, again, my name is Seth Vargo. I want to thank Eugene and Christopher. Their information is down here on this page as well if you want to connect with them on LinkedIn or Twitter. Thank you to Microsoft and HashiCorp for putting this together. As we said before, if there are any questions, we will answer those questions in email. So we'll summarize all of the questions and put out an email to everyone who's on the webinar here today, and we'll get that out to you hopefully by the end of the day today, if not early tomorrow. So thank you everyone for joining us, and thank you again to Christopher and Eugene for presenting and sharing their knowledge with us. Once the recording is done, we'll tweet it out and we'll make that available to all of you as well, and you'll be free to share that with your coworkers, colleagues, and friends. Thank you so much for joining, and have a great day. Thanks.